Okay, so let's start with a brief introduction before the real lecture material. Okay, so I just wanted to, I usually like to give a perspective for this course. Okay, so hopefully you all know about integrated, something a little bit about integrated circuits. An integrated circuit basically means you have multiple electronic devices on a single substrate, and that's a semiconductor chip. And they're all interconnected together to perform some useful functions. Okay? So the very first integrated circuit was demonstrated by Jack Kilby, who won a Nobel Prize for that work. And it was actually demonstrated using germanium as the semiconductor material. So there was a transistor and some resistors on a piece of germanium, this unattractive thing, and then all the wires, but all the wires were not integrated onto that same substrate of germanium. And that integrated circuit was about a thumbnail in size. So soon after that, Robert Noyce, who then was at Fairchild Semiconductor, demonstrated an integrated circuit using silicon as the semiconductor material. And again, there's a transistor and some resistors, but there are also, in this case, wires. So these shiny lines are the wires that interconnect those components to make it a useful circuit. Does anybody recognize the name Noyce? And what is he known for? Intel, yes. He co-founded Intel with somebody else. Who was that somebody else? Bob. No, Gordon. But yes, Gordon Moore. So in the first homework assignment, you know, I haven't covered that much. So I'm asking you to read Gordon Moore's first paper, original paper, that led to Moore's law. That's on B-space. And then another presentation that Gordon Moore gave about 10 years ago. So in other words, decades after his initial 1965 paper, you also have to go through that to do your first homework assignment. So the first integrated circuits in the late 1950s, basically the industry was able to advance the technology a little bit every year. And so you can have more and more components manufactured with reasonable yield. I mean, so you can get them working on a chip. And this has steadily gone at this pace of advancement. Basically, this pace of advancement has been sustained for over 4 decades. So Moore's law today is broadly refers to the rule that the number of transistors on an integrated circuit chip doubles every 2 years or so. And the chip price, the cost of that manufacturing a chip is about the same, doesn't change much. And so this chart, I know you can't read it in detail, but it's basically a plot of the number of transistors on a chip, and this is a log scale. So each increment is a factor of 10 with time. So the only thing I wanted you to see is that basically we're still staying on this trend decades after Moore made his first observation, and that there's no sign of slowing down for a while. Yes, Louis? When do I think it's going to stop? Okay, so there's 2 things that I think Gordon Moore himself said. Moore's law started like in the 70s. I mean, it was an observation, and then the industry started to pay attention to this, and they realized that they were indeed making exponential increases in number of transistors per chip over time. And then in the end, the industry set that as a benchmark for themselves. Right? So it became a self-fulfilling like prophecy kind of a thing, because basically industry said, okay, we need to advance the technology this much in order to double the number of transistors on chip in 2 years. So basically that's how it ended up being a law, but it's more like that's just the roadmap that the industry set for itself. So there is something called the International Technology Roadmap for Semiconductors, ITRS for short. That's updated every 2 years and is available online. Maybe I can add a link to that on the class website. Basically, that roadmap always paints like, okay, how small do the transistors have to get every year? And it always goes out 15 years. Okay, so when I was a student, it went out to 1990s, or mid-1990s. Today, it goes out to the year close beyond 2025. So interestingly, I was just at a research center meeting yesterday, and we asked industry participants, okay, how long do you think Moore's law is going to last? How long do you think silicon technology will continue to advance at the same pace? And they basically said, they all agreed, even Intel, at least 15 more years. But you might wonder, okay, your career's, okay, in 15 years, you're still going to be young and energetic, and you're still going to be working, right? All that means is that maybe transistor scaling and packing more transistors on chip, that might eventually slow down. It will still continue, but it just might become so expensive that the rate at which you advance the technology will be slower. We'll find other ways to enhance the performance or lower the cost per function. So that just means that there'll be other ways. So as an example, the industry, the display industry, making these flat panel displays, like now even for TVs that are really nice and thin, that industry, they have 1 transistor per pixel, per picture element. Okay, so that's an example of a integrated circuit in technology or industry where they don't shrink the size of the transistor with each generation of technology. Instead, they actually grow the size of the chip with each generation of technology, right? So to sell more and more products. So, and they come up with ways to make the manufacturing process even cheaper so that your TVs can be more and more affordable every year. Right? So same thing for the semiconductor integrated circuits. Maybe in the future, they'll come up with different ways to lower the cost per function. Rather than making transistors smaller so you get more per unit area, you might have to come up with cheaper ways to make transistors, this kind of thing. So there'll be plenty of jobs, opportunities, and certainly silicon integrated circuits, people will always come up with new applications for them. So even if the technology doesn't advance so quickly, people will still be able to develop new products and design them and sell them. You'll still have plenty of jobs if you study this field, right? If you work in this field. Okay, the most advanced integrated circuits technology today is at about the 20 nanometers minimum feature size. This is just an example. So integrated circuits are fabricated on wafers, single crystalline wafers of silicon. So I brought an example of one here. You might want to take a close look at the edge to see that there's something missing at the edge. But anyway, so that's an example of a wafer. It's less than a millimeter thick. The diameter used in the most advanced fabrication facilities are 12 inches in diameter. Okay? And they can hold hundreds, if not thousands, of integrated circuit chips that are depending on the size of the chip. So this is just an example of a microprocessor chip that Intel manufactures. Okay, so this is another way to look at the impact of Moore's law. It's not, transistors, number of transistors per chip. The average person, if you go out and tell them about that, it doesn't mean too much to them. But if you show them a chart like this, okay, how about the number of computing devices that has been sold because they're affordable over time. So again, this is a log scale, right, showing exponential growth per decade in the number of computing devices in the world. And you can see with each decade, you have emergence of some major new thing like the personal computer or desktop internet, or nowadays we're in the age of the mobile internet. So the number of devices is growing exponentially. So in the future, we expect within the next couple of decades, trillions of devices, computing devices in the world. So they'll be pretty much embedded in us, in our environment, and so on. And they have a lot more functionality than just computation, right? So maybe we'll touch upon some of the other functions of semiconductor devices throughout the course of the semester. Okay? And this has all been enabled by this virtuous cycle of shrinking down the size of the transistor to, it turns out, integrated circuits operate faster when the transistors are smaller, and we'll go over that and the reason for that. And it turns out to be lower cost per transistor, therefore lower cost per function. And that allows new products to be designed and sold, because people can afford them, and people make money, companies make money, they invest some of that profit back to advance the technology to scale and shrink things more. And so today, as I mentioned, it's about 22 nanometer minimum feature size, and it's only going to continue at least for another 15 years or so. So how small is a nanometer? Well, this is just a log scale, just showing you like some examples of things in nature that are small. So DNA is on the order of 1 nanometer. And so there are biochips, or it's biodetectors or biosensors, biomolecular chips that are made using the same manufacturing techniques used to make integrated circuits to basically sort DNA or to detect certain strands of sequences of DNA. So a transistor is on the order of a couple tens of nanometers. Over the next 15 years or so, we expect it to scale down closer to be below 10 nanometers. Okay? Now, on your homework, so I'm giving you the homework because so that you can see what's expected of you in this class, so you can decide to drop it if early, right? Because even sometimes I'm disappointed that even on the final exams, some students haven't remembered that a micron, because usually these devices are so small, we typically don't talk about distances or, in meters. We talk about centimeters, if not microns or nanometers. So you should be easily able to convert units, okay, between micrometer, nanometer, centimeter, okay? So don't forget those for your homework and for the quizzes. Or you can put it on your cheat sheet. Okay, so in this class, basically, you're going to learn about semiconductor device physics. Okay, so it's not really high level. It's more like digging down deep, understanding what's going on with electrons and atoms inside the semiconductor. So we do need to spend some time to cover the fundamentals of semiconductor materials, fundamental properties, why they behave the way they do, and how do we keep track of what's going on in a semiconductor. So that'll take 3 weeks. Then, okay, so ultimately you want to understand how a transistor works, right? So a transistor it has a gate electrode that is used to control the current flowing between two conductive source and drain regions. And it's isolated from the semiconductor surface by a thin oxide material. So this is why we call it metallic gate oxide semiconductor field effect transistor. So in order to get current in and out or to apply voltage to this device, we need to put metal wires in contact with the semiconductor. Okay, so you have to understand how a metal to semiconductor contact works. So that's really basic, so we'll cover that first after semiconductor fundamentals. After that, then we'll cover how a p-n junction diode works. And this is good for understanding how optoelectronic devices work, like solar cells, light-emitting diodes, and so on. And it turns out these source and drain regions form p-n junctions. So it is important to understand how a p-n junction works before you can understand how a transistor works. Then the heart of the transistor is the metal oxide semiconductor stack. So you do need to understand how a MOS capacitor functions. And then we'll finally get to the MOSFET. And we'll talk about modern MOSFET technology. So you'll come all the way up to speed on modern integrated circuits technologies here after all these weeks. And then you should be able to dive into your design project. And for the final couple of weeks, we'll just cover the bipolar junction transistor, which actually does have applications for higher gain amplifiers and high-speed circuits. But actually, if you go from the source to the semiconductor to the drain, that's actually a BJT transistor as well. So inherently, a BJT transistor is a parasitic component of a MOSFET. So it is important to understand how a BJT works, even though they're not the primary device used in integrated circuits today. Okay? Any questions about the course content, whether or not it's going to cover something? I'm happy to take things out. Well, I can't, not really. But if there's some stuff that you're interested to learn about, I can try to squeeze it in. Pardon me? Modern devices. Yes, so modern devices will be in section 6. So you'll learn about like the 3D transistors, the silicon on insulator, and so on. Yeah. Yes? Solar cells. Yes, so solar cells will be covered when we talk about the p-n junction diode. Right. Solar cell is a p-n junction diode. Okay. Anything else? Yes, Ali. Nanotube transistors. Oh, okay. Sure. Okay. Why don't I plan to mention something about nanotube transistors when we talk about modern CMOS transistors? Okay. Good suggestion.
When we're doing design, will we be doing like simulation?
Yes. So the design project involves running a computer simulation program, as industry standard software. So you will have to get an instructional account. So what I found last semester is that in the first lecture, I gave out all the account information, and then later when the project was, when people had to work on the project, somehow people lost all their account information and all this. So I'm just going to hand it out later in the semester when you've decided to stay and you found a partner and you can figure out who really needs the account, okay? Yes, but it is industry standard because it is very expensive to run a lot of experiments, to try to make a transistor and then see how it works And that takes usually months, turnaround time, or if not weeks, even in the most advanced fabs. And you don't really want to, and it costs a lot of money. So today, a lot of companies use these technology, computer-aided design tools, not only for designing circuits, but for actually fine-tuning the fabrication process, to fine-tune their transistor, just to make sure they have a good chance of having it work when they go through the fab. So you'll be using basically the same software that the industry uses. Okay? Any other questions? Okay, let's get started. So let's start with the real meat of the course. I don't think I didn't write anything here, did I? Okay. All right. Okay, so let's start with the lecture. So I don't really write very well on the screen, just to let people who are watching this on webcast know. So usually what I've done is maybe in the evenings after my lectures, I'll write them more neatly and post the neater marked up notes on the website. Okay. All right, so today let's just, if you want to stretch, that's fine. But today let's just cover some really basic, start covering the semiconductor fundamentals. Just understanding why silicon or semiconductor materials actually are semiconducting. Okay? So the first thing is just to make sure that you have handy these fundamental constants, the values of these fundamental constants. So electronic charge, so that's the charge, the magnitude of the charge on an electron. So in this class, you don't really need to keep track of more than a couple of digits of accuracy. Okay? So 1.6 or 1.609 is fine. Just 1.6 times 10 to the minus 19 coulombs is fine for electronic charge. Permittivity of free space, 8.85 times 10 to the minus 14 farads per centimeter. So I want to point out that in this class, we actually generally will talk about volumes or dimensions in centimeters. Okay, it's not meters. So pay attention to that, so that your answers are not an order, 2 orders of magnitude off. Boltzmann constant, K, just little k, 8.62 times 10 to the minus 5 electron volts. So units of energy in this class, it's just convenient to use electron volts rather than joules. And the difference between an electron volt and a joule is just the same magnitude as that electronic charge, 1.6 times 10 to the minus 19. Okay? So just later you're going to be doing calculations for homework. So just keep in mind that for energy, we always try to keep track of energy in electron volts, not joules. Planck constant, notice also, energy is expressed in electron volts. For mass, we really don't use mass too much, but okay, kilograms is fine. Okay. All right, so some important quantities just to keep in mind. This KT, so T is the absolute temperature. Room temperature is, in this class, 300 Kelvin. Okay? So KT over Q at room temperature is 26 millivolts. Okay, so pay attention to the units. KT is 26 millielectron volts. And if you divide by Q, that becomes 26 millivolts. Okay? So this is something that I expect you to remember for your quiz, because to do calculations very quickly, you'll see in a couple of weeks why. Okay? And another thing that's very useful to know is that KT times the natural log of 10, because we do a lot of humans, we like to plot things on log scales, orders of magnitude. That's base 10, but a lot of physical phenomena happen with exponential factors. So we need to often convert from log base 10 to natural exponential. So KT times the natural log of 10 is often used. So keep in mind, KT times the natural log of 10 is 60 millielectron volts at room temperature. Okay, so what is KT over Q times the natural log of 10? 60 millivolts, that's right. Okay? All right, so those are just up front, so I just want to make it handy so there's one slide that contains all the values of those important constants. Okay, so let's get started. So what is a semiconductor? Well, semiconductor is a class of materials whose conductivity, in other words, how easily current can flow through it, actually can be changed, can vary over a wide range. Okay? So in nature, if you look at all the materials in nature, there are classes of materials that are very conductive to electricity. They have what we call low resistivity. We'll cover resistivity in a couple of weeks. But resistivity is a measure of how resistant a material is to electrical current conduction. So if you have low resistivity, then the material is considered to be a conductor, a good conductor. So let's talk about resistivity. Typically in the range 10 to the -5 to 10 to the -6 ohm centimeters. So later we'll give you a formula for resistivity. But this is just to give you an idea of the wide range of conductivities of materials in nature. So that's for a good conductor. So a good conductor used in integrated circuits. Does anybody want to guess what kind of good conductors we use in integrated circuits today? Aluminum, that's right. That was the most popular one. And in the recent 15 years or so, we've moved to another, even more conductive material than aluminum, copper. That's right. So copper is the most common. It's used for most of the layers in the most advanced integrated circuits today. But aluminum actually is still used for some layers. Okay, so you have so many transistors packed into a small area. You need many layers of metal to interconnect them all. Some of those layers are aluminum, but most of them are copper today. Okay. Now, on the other end of the conductivity spectrum, or resistivity spectrum, is an insulator, just to give you an idea. So resistivity is in the range of 10 to the 14 to 10 to the 18 ohm centimeter. Okay. So the point here is to show you there's orders. When I say like there's a huge difference in electrical conductivity of materials in nature. This shows you, we're talking about more than 20 orders of magnitude difference in ease of current flow between different types of materials. So intermediate, okay, so semiconductors are in between. Okay, they're neither super good conductors, but neither are they very good, super good insulators. But they can span that range. Not quite the entire range. For a semiconductor, you can go from 10 to the -4 to 10 to the 4 ohm centimeter. Okay, so you can see it's intermediate to a good conductor, but if you really want an insulator, electrical insulator, you shouldn't use silicon. Okay. All right. So for silicon. Okay. So silicon is one of these semiconducting materials. It's a semiconductor. Another thing that's important is not only the intrinsic property of the material, but also the crystalline structure. Okay, so that's what we'll cover today. So if you sort of look at a material under a microscope, a high-resolution microscope, you'll see atoms arranged in some configuration. Okay, so in that wafer that I passed around, the atoms are arranged perfectly lined up with each other. In fact, okay. So if you were to zoom in, 100,000 times and looking at the silicon atoms, they'd be arranged like this. Well, yeah, sort of like this, if you could see them. So each atom is equally spaced from 4 other silicon atoms. I'll pass this around. So that's a tetragonal sort of bonding structure. Okay, so this is what integrated circuits are made with today, single crystalline silicon. On the other end of the spectrum, you have amorphous silicon. And amorphous silicon is actually what's used in flat panel displays. Okay, so when I said that there was 1 transistor per picture element in a flat panel display controlling the brightness, those transistors are made with thin films of silicon coated onto the surface of a piece of glass. And the silicon, because of the way you deposit the silicon on the surface, the atoms are not really well lined up with each other. Okay, but it's easier to put down a thin film of silicon if they're not lined, if the atoms don't have to be lined up with each other. It's faster, cheaper. And flat panel displays, you know, it has to be really cheap. I mean, you don't want to pay more than, what, $100 for a display? So that means the fabrication process has to be really cheap. So you want to deposit really quickly and not worry about lining up one atom to another. You can get away with an amorphous material. And a polycrystalline material is something in between. It's neither perfectly crystalline nor amorphous. There is some order. So atoms are locally lined up with each other, but not all across the crystal. Okay, so there's some regions where atoms are lined up with each other, but they're not really lined up with atoms in other regions. Okay, so that's polycrystalline. So the higher performance, slightly more expensive displays may be used for smaller, like handheld devices. Sometimes use polycrystalline silicon for these thin film transistors. Okay, so why are there these differences? So first of all, for integrated circuits, you have to operate them at high speed. For a flat panel display, a transistor only has to turn on like within a microsecond, or okay, let's say a nanosecond. So very short period. That's not that fast. For an integrated circuit chip, how fast do you think they have to turn on and off? Clock speeds, gigahertz, that's a clock speed, but the transistors operate much faster than the clock speed. So talking about like less than a picosecond, electrons have to move around and turn on and off a transistor within a picosecond. For thin film, flat panel displays, you know, even up to a microsecond might be good enough. So in other words, electrons don't have to move around so fast for displays, so that's why you can afford to make really cheap transistors. So let's do an example. So let's say, okay, so the reason why it's not easy, why is there a difference in cost? So does anybody know, have you learned how a single crystalline wafer is made? You'll learn this in EE130 if you take that class. Pardon me? Evaporation. Okay, so if you evaporate, let's say if you have a chunk of silicon, you heat it up and let it evaporate and let's say evaporate onto the surface of another wafer. That will give you either amorphous or polycrystalline material. This wafer was cut from an ingot. Let's just, yeah, they're cylindrical. Okay, so basically you start with a tiny seed of single crystalline silicon, which is up here, and you dip it into a molten bath of silicon, and you slowly pull it out. So it cools, and as it cools, the silicon solidifies, and you pull it out of the molten bath that's like being spun around for uniformity. You pull it out slowly, and you end up with ingots that are cylindrical like this. And the ingots, of course, are in diameter today as large as 12, slightly more than 12 inches in diameter. And then you slice them into pieces. But basically, you have this one huge single crystalline silicon ingot from which you cut slices, and all the atoms are lined up precisely with each other. Okay? That takes a lot of time, and it's more expensive. So a bare wafer without any integrated circuits formed on it is several $100s. Okay? Now, evaporation, you don't bother to line up one atom here on the substrate over there, because it's like all just sprayed at once. Okay, so there's no way you can guarantee that an atom here eventually will be perfectly lined up with an atom somewhere else. So it's like this. In this room, you know, the chairs are perfectly lined up this morning when I looked. But anyway, so if I asked you to line up the chairs perfectly, you know, in a regular order, you would have to sort of start like with one chair here, line it up, and line up the next, and so on, right? And rather than if I had like 5 people working, okay, please line up each row. Each row probably is not going to be perfectly aligned to the other rows, but it will be aligned within the single row. So that'd be like the polycrystalline example. But which one's faster? If you have one person doing the entire row, the entire room, you get a perfectly aligned, you know, set of chairs, but it's going to take longer. It's more expensive, right? So basically, that's the reason why this is cheaper. Amorphous is cheaper compared to crystalline. But for crystalline, okay, so we need crystalline for fast, high-speed circuits. So let's say if I'm like an electron and I want to run through the room, if you're all lined up, then it's easy for me to run. But if you're all like messed up like back there, it's going to be taking me longer to run through the room, right? Same thing. Electrons will move faster, zoom faster through a crystalline lattice if all the atoms are perfectly aligned versus all like haphazardly aligned in an amorphous material. Okay, so there's a trade-off between performance and cost. So in engineering, when you do the design project, you'll learn this, many trade-offs. That's what engineering design is all about. You have to design a system or a device to meet some requirements within some constraints. Right? So the constraint for flat panel displays is cost. Constraint here for integrated circuits is performance, right? So that there's trade-off between, you can't have a low cost, super low cost, and super high performance. Okay, so let's look at the various semiconductor materials that are used in industry today. Okay, the most common semiconductor materials. Okay, so we're looking at a section of the periodic table of elements here. Column 4. Oops. Okay. Column 4 is here. Oops, I can count. Okay. 5 and 6 and 3 and 2. Okay? So these, did I label it wrong? Okay. So what does these numbers represent? 2, 3, 4, 5, 6. Number of valence electrons. Excellent. So the outer shell or a partly filled shell, how many electrons are out there? Very good. Okay. So the nice thing about semiconductors is that they have valence electrons and can easily form bonds with other electrons. Okay. So an example, somebody wanted me to cover carbon nanotubes. So yes, carbon is a semiconductor material, like carbon nanotubes or graphene. Well, actually, a special kind of graphene. Okay. So it turns out that carbon is only a semiconductor material if you make it really small, like a carbon nanotube with a very small diameter, or graphene ribbon, nanoribbon that's very narrow, like 1 nanometer wide. But carbon can be a semiconductor material. The most common semiconductor material is silicon. It is the most common element other than oxygen in our Earth's crust, more cost effective. And then there's also germanium. Like I said, the very first integrated circuit was demonstrated with germanium as a semiconductor material. Okay, now we can also combine elements to form compound semiconductor materials. So, for example, we can make silicon carbide transistors. So, has anybody heard of silicon carbide? Silicon carbon basically is used for high power or high temperature. Like if you want some electronic devices that can withstand hundreds of degrees Celsius and operate under harsh conditions, silicon carbide is your material. It's more expensive, of course. But this is an example of a compound of common 4 elements. Gallium arsenide is a very common 3,5 semiconductor material that's used for optoelectronic devices. Okay? And we'll talk about that later. How about an alloy? So an example would be silicon germanium. Okay, so the difference between a compound and an alloy. In a compound, you have one silicon atom, let's say in a silicon carbide, one silicon atom for every carbon atom. It is lined up very well in an arranged manner. But for an alloy, they're completely miscible elements, so you don't have to have one germanium atom for every silicon atom. You can have any ratio of germanium to silicon in that material. So silicon germanium is used in the most advanced semiconductor devices today. They're actually used in the source and drain regions of the transistor. And in the future, they might be also used in that middle region controlled by the gate electrode. So silicon germanium is very common. And then for the compound optoelectronic devices, instead of gallium, you could have an alloy of aluminum and gallium. So like this. So rather than just one gallium atom for every arsenic atom, you can have either, some of them can be replaced with aluminum. Okay, so if you have an alloy, you can actually adjust some of the electrical properties of the semiconductor, tune it to. So for example, if we can, during manufacturing, control the percentage of germanium in a silicon germanium material in the source and drain regions of the transistor, we can actually control the lattice constant, the spacing of the atoms, and induce stress in the transistor to enhance performance. Yes, question?
So the alloy is still crystalline?
Yes, so the alloys are still crystalline. They're grown So that's a good point. So the average atomic spacing is actually a few percent difference. It could be quite different between the different semiconductors. So if you tried, so that's a constraint. So that limits how thick you can grow these alloys on top of, like if we wanted to grow silicon germanium on top of silicon, we can't make it too thick because the lattice mismatch eventually will build up so much stress that we'll want to leave and form crystalline defects. But yes, in principle, we try to make these single crystalline materials also. So the the compound semiconductor alloys are used to tune the properties of optoelectronic devices. So like for a light-emitting diode or for a solar cell, you want to adjust the absorption spectrum, or you want to adjust the color of the light that emits. You can change the concentration of these elements. Okay? All right, so let's talk about silicon. So this is like the background you need to, so hopefully you remember that things are made of atoms and the hydrogen atom, actually we sort of use that simple model. Hydrogen atom has a nucleus with a proton and a single electron orbiting around it, and that electron can only have certain allowed energies. Like when it's orbiting around the nucleus, it can only have certain allowed orbits with associated energies. The same thing with any other material like silicon. So silicon actually has, 14 electrons, but 10 of them are actually filling the first two shells, electron shells in the orbits here. So the first two shells are completely filled. The 1s shell is filled with 2 electrons, and then the second shell is filled with 8. And so basically this sort of acts as the core, right? So this is kind of like the core of the silicon atom. And then the valence electrons are sort of farther away from the nucleus, okay? So they're sort of less closely tied to or bound to the core. So you have 3, where is it? 3, right here. 4 electrons, 2 of them nominally 3s, and 2 of them 3p. So what happens is to minimize the energy of those outer valence electrons, the s and p orbitals sort of hybridize. So we call them 4 sp orbitals in the outer shell, in the outer orbit. Okay. Oh, so here are the valence electrons. Those electrons are the ones that participate in electrical conduction and bonding, covalent bonding with other atoms, other silicon atoms, or impurities in the crystal. Okay. So I just said that. Okay. Is there anything else? Yeah. So each electron, so each of these 4 hybrid sp orbitals can form a covalent bond with a neighboring silicon atom. And that's why every single one of these silicon atoms is bonded to 4 nearest neighbors. Okay? All right. So how do we describe this crystalline structure when we like make devices? Okay, so let's talk about, first of all, how do we describe this silicon crystal structure? Has anybody learned about Miller indices in a material science course? Okay, so this is a little bit of review. So if you were to describe the arrangement of atoms in a silicon crystal, all you need to do is to describe a basic unit cell. Okay? So for example, okay, I'm going to draw on the board, so this is not good for people watching on webcast. Let's say if I have some material, the atoms are arranged in a nice cubic, 3-dimensional lattice. So all the atoms are equally spaced from each other, connected to 4 nearest neighbors. This is a 3-dimensional lattice, right? So you have x, y, and z directions. So each atom is connected to, 6 nearest neighbors. Okay, so let's just look at a 2D crystalline structure. Okay, so the atoms are arranged very regularly, like this, in a single crystal. If you want to describe the arrangement of atoms to somebody else, all you need to do is to describe the unit cell. Okay? So a unit cell is basically something that you can describe, and you would repeat it you know, in all directions. So to the right, to the left, up and down, and to the sides. So all you have to do is just describe what's in a unit cell, and the person would know to replicate the crystal structure. You just repeat it in all directions, right? So here, a unit cell could just be a single atom in the middle of that rectangle. And that's an example, right? Now, a unit cell could also, in this case, you know, it's kind of arbitrary. You can define a unit cell to be consisting of 1/4 of the atom in each corner, right? So the definition of unit cell is a little bit arbitrary, but in any case, the key thing is that somebody could reproduce the entire lattice based on that one unit that you give them. So the unit cell for a single crystalline silicon material is shown here on this slide. So this is the so-called diamond cubic lattice structure. So it's cubic. In other words, if you draw a cube, you have atoms at each, you have atoms at each corner. Okay, so just like this red unit cell, you have an atom at each corner, right? So, except now it's in 3 dimensions. So that's why it's called cubic. So you have an atom in each corner. You also have atoms at the center of each face of the cube. Does that make sense? Oh, it's hard to see here, but there's one atom along each cube has the unit cell is a cube equal. Okay, so it's equal. It's not drawn. It doesn't look quite equal here, but this is the lattice constant A. Okay, so it's a cube. So each of these dimensions is A, and the lattice constant A is 5.431 angstroms. Okay, so it's a perfect cube. You have atoms at each corner. What percentage, what fraction of this atom is inside the cube? 1/8. Very good. And what fraction of the atom on the faces is inside the cube? 1/2. Okay, so half in, half out. Now, in addition, you have 4 atoms inside the cube. So here's one. Okay, and okay, so let me just use this. I thought I could change the color, but maybe not. Okay. Here's one that's inside the cube. Here's another one that's inside the cube. Is that right? Okay, wait. Yes, and then here's another one inside the cube, and another one completely inside the cube. So there are 4 atoms completely inside this unit cube. Okay, so remember, just look for a tetrahedron kind of thing. So it turns out that these interior atoms, if you draw a cube diagonal, okay, so if you draw a diagonal from this corner all the way down to this corner, oops, maybe I didn't draw it right. Where is it? Oh, okay, wrong diagonal. You draw a diagonal from this corner down to this corner, you'll see that you have an atom 1/4 of the way down. Okay? Oh, and I did draw it correctly here. So here's another diagonal here. There's an atom 1/4 of the way up. Okay, so there are like 4 cube diagonals, and the interior atoms are like 1/4 of the way along the cube diagonals. Okay, so remember there's 4 interior atoms, 6 face atoms, and 8 corner atoms. Okay, so there's 4 here, and we have 8, and we have 6. And so how many atoms? So this is, okay, so this is 4 atoms per cell. This is 1 atom per cell. And this is 3 atoms per cell. And we know the cell volume. Okay, so this is 1.6 times 10 to the minus 22 centimeters cubed. So notice that when we talk about volumes, like number of atoms per unit volume, the unit of length is centimeters. Okay, so in this class, we're talking about volume amount, densities. We always use centimeters. So the density of silicon atoms is 8. And so total is 8 atoms per cell. And so it's 8 over 1.6 times 10, oops, times 10 to the 22. Oh, minus 22. So this is equal to 5 times 10 to the 22 atoms per cubic centimeter. Okay? So this is a number that you actually should know or remember. Okay, the atomic density of silicon. Okay, because later we're going to be talking about introducing impurities in very controlled amounts, and of course the controlled amount is going to be less than 5 times 10 to the 22 per centimeter cube. Okay, so this is important. You know, in this class you slowly have to remember orders of magnitude of various quantities, and this is one. Yes, question?
It's atoms per, what is the last two letters you wrote there?
Atoms per cell.
Per cell.
Yes, per unit cell.
That's at the very bottom there, is just the last.
Oh, this is per cubic centimeter. Sorry. Yeah, cubic centimeter. Like I said, I'll probably post neater notes online. Okay, so the compound semiconductor devices, like gallium arsenide, they have a similar structure as silicon. They have a similar unit cell. Of course, the atomic, the lattice constant will be slightly larger, because those are larger atoms. But if you look at the arrangement, you can see that every other atom that's connected to each other, that's bonded to each other, is either gallium or arsenide, or arsenic. Right? They're just alternating. Okay? But this is called a zinc blend structure. And I forgot to mention that for silicon, we call it a diamond cubic lattice, because diamond has the same atomic structure. Okay, so finally, let's get to crystallographic notation. So how do we specify which direction electrons are flowing, or which direction we're fabricating devices in the integrated circuit? Okay, so why do we care? Actually, yeah, the question is, why do we care about directions in a crystalline semiconductor? Densities, that's true. Okay, so the atomic density in different directions is different. That's absolutely true. Yeah, so there are, exactly. So because the atomic density is different in different directions, and the covalent bonds are oriented in different directions, the conduction of electrons is different. The mobility of electrons, how easily electrons move through the crystal, is different in different directions. And so it is important to keep track of which direction your transistors are forcing electrons to flow in the chip. Okay, so did anybody notice something weird about the edge of this wafer? It had a notch, exactly. So the notch here is so that during the fabrication process, when the wafer is inserted into a piece of material to define the orientation, the layout orientation of the transistor, it will orient the wafer exactly right so that the transistor will be laid out in a direction to maximize the mobility of the electrons. Okay, so it is important. Okay, so this is the notation, crystallographic notation. It's pretty simple. It's easiest to illustrate with a simple example. So let's say you're interested to talk to people and specify this particular plane, this particular direction in your single crystalline silicon sample. So all you need to do is to give them a set of 3 numbers, and we call them HKL here. Okay? And these 3 numbers, to get these 3 numbers, you need the x-intercept, the y-intercept, and the z-intercept of that plane. Okay, so let's just write down those numbers. So let's say the x-intercept, the y-intercept, and the z-intercept, if I can write this. Okay. See, that's all you need to let people know like which plane you're talking about in this structure. Okay, in the lattice. So what is the x-intercept here? This is x, y, z. So what is the x-intercept? It doesn't intercept, right? So it's infinite. All right. How about the y-intercept? It's just equal to the lattice constant. All right, let's just assume this is the lattice constant. So we express the intercepts in units of the lattice constant. So this y-intercept is like 1 atomic lattice constant. And z-intercept, infinite. Okay, but notice the definition here of the Miller indices, it's the inverse intercept. So this plane is going to be the, what is it? The 0, 1, 0 plane. Okay? And so you use these parentheses to indicate a specific plane. Now, if you look at the crystalline, the atomic structure, you know, if you turn this cube around, you really can't tell any difference, I mean, in terms of atomic density and the arrangement of bonds between any face. All the faces of the cube have the same atomic arrangement, right? So for electron transport, they're all similar. Same thing, like there are multiple diagonals. You know, conduction is going to be similar in all of those directions. So actually, that's what we call equivalent planes. So if we're talking about a family of equivalent planes, then we use the braces, the curly braces. Now, sometimes we care about specific directions within the silicon lattice. And so we, again, use the same indices, except now we use square brackets or for a specific direction, or pointy brackets for a family of equivalent directions. And the easiest way to remember that is that the direction is perpendicular to the plane. So if I want to specify the 0, 1, 0 direction, it is the direction here, 0, 1, 0. Right, so just that's the easiest way for me. I just remember. So you're looking at a direction that's orthogonal to the plane. That's the 0, 1, 0 direction. Okay? All right. Pardon me? Equivalent, okay. So equivalent means that you really can't tell any difference in the arrangement of atoms. Right? So if you look at one face of this unit cell, look at the arrangement of atoms along like a 0, 1, 0 plane versus a, what is this, 0, 0, 1 plane. You know, the arrangement of atoms is exactly the same, right? The density and the bonds and so on. So it's just as easy for an electron to move along a 0, 0, 1 plane versus a 0, 1, 0 plane. Yes, 0, 2, 0 would be like going, oh, okay, yes, so that's a good question. Okay, so 0, 2, 0 would be like going right down the middle here. But usually, yes, that's true. But usually we don't define so many planes. So the planes that we care about most are shown here on this slide. Okay, a 100, 110, or a 111. And so for the first homework assignment, you'll be asked to figure out, okay, what is the density of atoms along each of these planes, to give you an idea of which plane is it easier for electrons to move in. And I'll tell you that this surface of the silicon is a 100 surface. Okay? And the direction, this notch indicates a 110 family of directions. Okay, so anyway, there are reasons for that. Okay? And so in the old days when we had small wafers to make integrated circuit chips, we just had a flat to indicate the direction. So the silicon crystal is grown so that each wafer has a surface of 100, and then we care about the direction that we make the transistors in. So we want to indicate the 0, 1, 1 direction. And today, now if you cut a flat into a large wafer, you actually are wasting silicon. You can make a lot of dies there. So that to save area, to make more chips per wafer, they just change to a notch. Okay? So the way you make integrated circuits is that you take a wafer and you stick it into a process chamber or some kind of a lithography tool. The first thing they do is they rotate the wafer around to orient it to go in, to define the features. And what they do is they have like a little laser at the edge, and then when the laser passes through to the detector, then it stops rotating. Right? That's how they orient these wafers. Okay, to make sure that everything's lined up. So there used to be an applet that was available online, so you can actually grab with a mouse, this cute unit cell and play it and move it around, just so you can see the different. Look at the unit cell in different directions, and unfortunately that seems to not be available anymore. But anyway, these are views in different directions. Okay, so generally a plane with lower density of atoms will make it easier for electrons to flow through. Okay, and all right. Okay, so let's talk about the final thing, and then we'll continue next time. So what makes silicon a semiconductor? Well, if it's pure, it's perfectly crystalline and no defects, it's pretty resistant to current flow. Not that many electrons that are free to move around naturally in silicon. There's two types of mobile charge in silicon to conduct current. So current is just charge moving per unit, like how many charges cross per unit area, a certain location. So you have conduction electrons. So electrons that escape from the covalent bonds, they can move around freely in the lattice to conduct electricity. And if you have an electron that escapes from a covalent bond, that means you have a half-filled covalent bond somewhere. That means you have some positive charge associated with that half-filled covalent bond. And that half-filled covalent bond can actually move around. And that can be mobile. So those are the two types of mobile charges, okay, in a semiconductor. You have negatively charged electrons and positively charged holes. And the way that you can change the resistivity of a semiconductor device is by changing the temperature, okay, to make it easier for electrons to escape a covalent bond, so there's a lot of electrons and holes around to conduct current. Or you can add impurities called dopants, and we'll talk about that next time. Or you can apply an electric field. An electric field exerts force on a charged particle, and that force can be enough to pull the electron out of the covalent bond so that you can create electrons and holes to conduct current. Or you can shine light or even higher energy radiation to give an electron enough energy to escape the covalent bond to move around. Okay? So this simple bond model, basically, this is basically the core, right, that I mentioned earlier. And what we're only drawing is the valence electrons. And so each silicon atom shares a valence electron with the nearest neighbor. So it sort of sees on 8, sort of a full shell, and 8 valence electrons altogether. And what happens when you heat it up or shine light or something else or apply electric field is a covalently bonded electron can escape, leaving behind a hole. And this electron can move around, okay? And the idea here is that, okay, so let's say we have this hole here. So electron can move over here, leaving behind a hole. And then later, let's say this electron can move over here to fill that half-filled covalent bond. So the hole ends up here. So wherever there's a hole or missing electron from covalent bond, there's a positive charge, net positive charge there, right? So that positive charge can end up moving, right, eventually around in the lattice. Okay, so this is why a half-filled covalent bond is mobile inside a semiconductor. And that's why we can keep track of it as a mobile mobile positive charge. Does that make sense? Okay. Okay, and so how many electrons and holes naturally exist in a semiconductor? Well, in a pure semiconductor, every time you free an electron from a covalent bond, you leave behind a hole. So the number of electrons and holes has to equal each other in a pure semiconductor. And the likelihood that an electron can escape a covalent bond increases exponentially as you heat it up. So here's a plot of the intrinsic hole and electron concentration as a function of temperature. And you can see it increases exponentially as you increase the temperature. And the thing you need to remember just from one key number, at 300 Kelvin, that's room temperature, the intrinsic concentration of electrons is equal to the intrinsic concentration of holes. This is n sub I, and that's 10 to the 10. So that's a nice round number to remember, okay, at room temperature. And so this is just definition of terms. N is the concentration of negatively charged mobile carriers, that's electrons. P is the concentration of positively charged mobile carriers, holes. And if it's a pure semiconductor, it's always equal to Ni, the intrinsic carrier concentration. Okay, so that's just terminology. And that's it. So the summary slides just summarize what I said. All right, so I look forward to seeing you on Tuesday. Have a good Memorial Day or Labor Day holiday.